Let's check out the answers to this. There's a lot of really important things that will come out in part of this practice. Some things that we only really run into when we're working the problems. So follow along with me. I know it's not the most exciting thing to look at the board, but please do. It's important. All right, so check out my position versus time graph that I have there. You should have had one that looked exactly like mine. And I want you to note, check out how it starts right here at position 2 centimeters. I should have labeled that. We have centimeters going up, and we have seconds here. It starts at 2 centimeters. So I'm going to draw my line as best fit, going through all those. And what do you notice about that line? I notice that it's straight, and we know, and we found this in our notes from the bubble tube lab, that when we have a straight line, it's going at constant speed. We call that, it's a linear line, and it's constant speed. Great, fantastic. This is also telling us that as it starts right here, my starting position is 2 centimeters. Now we haven't talked about position yet, but think about it. If I'm standing in the front of the room at an X on the spot, and then I walk around the room and it takes me about 50 paces to get around the room, and I get back to my same X on the spot in front of the classroom, have I changed positions? No. I haven't changed any positions. I'm back in the exact same position, but I've traveled 50 paces. My distance was 50 paces, but my position remained the same. We're going to see that this concept of position is a big idea coming up here. All right, so its starting position is at 2 centimeters. It's almost like saying if you were running the 100-meter dash, you would be at the start line, which was 0, but your buddy was at 2 centimeters in front of you. They're getting a head start. Okay, now let's look at 1B. 1B is actually asking this. What is the position of the car at 3 seconds? Well, let's just look at this part right here. At 3 seconds, I can do that. I can go to my time and look at 3 seconds, and I'm going to circle that in green. At 3 seconds, I'm at 8 centimeters. That's my position. It'd be like saying you're driving to Chicago and 2 hours in, you're at Champaign, Illinois, right? It's just where you are at that time. At 3 seconds, I'm at 8 centimeters. So I'm going to do the same thing at 5 seconds. At 5 seconds, I'm at 12 centimeters. All right, that's just where you are at that time. Awesome. Now the next one, 1C, is asking us how far did the car travel between 3 and 5 seconds? All right, let's check this out. If we start at 8 centimeters and we go to 12 centimeters, aren't I having a change of position of 4 centimeters? All right, I want to show you how we found that. I know it seems like simple math, and it is, but we actually just discovered our very first formula. So check this out. We just got the answer of 4 centimeters. Of 4 centimeters, sorry about that. And we started with 12 centimeters minus 8 centimeters equals 4. Now I know that's simple math, and you're like, why is she writing that on the board to get that? But check this out. At 12 centimeters, this is my 5-second position, and this is my 3-second position. Now, just like we were talking about the other day, no one goes around and saying, hey, I'm positive 14 years old. We don't put the positive in there. We just say I'm 14. But it's understood that you are positive 14 years old, or you are positive 15 years old. All right, so this does come out to a positive number. All right, in physics, we know that position, when they're doing formulas in physics, P was taken. So position is actually denoted as an X. X equals position. So when we go back to our position time graph back here, I should come back to here real quick. This is actually a X versus T graph. X versus T. Here's how we got that. If position is known as X, P was taken for some reason in science when they were doing that. So when we talk about position, we're talking about X. I know that's totally contrary to what you've learned in algebra, but when we say position from now on, we're going to say X. I know in algebra, you used to have X down here on the bottom line. But when we have position time graphs in physics, x is on the vertical axis, right there as you see it. We're going to talk about time in terms of t. So we've got time for t, position for x, so this is an x versus t graph. So going back to what I was just talking about, we just discovered our very first formula. Back here. If x equals position, when we take 12 minus 8 and get 4 centimeters, we know that's a positive number. We're actually saying our final position minus our initial position is equal to our change of distance. Now in physics, whenever you see that triangle, that means change. Distance is represented by a d. This is the very first formula, that we have here in physics. X final, my final position, minus my initial position is equal to change of distance. Now I got a question. Could I have done it this way? 8 centimeters minus 12 centimeters is equal to 4 centimeters. Could I have done that? No, I couldn't do that because check this out. Isn't 8 minus 12 centimeters actually a negative number? And we didn't come up with a negative number. We came up with a positive number. And if we go back to our graph, one thing coming back from the other day, we've got a positive slope. You guys remember that slope has speed, width, direction? This is telling me that I'm going in a positive direction. So I'm going to have a positive number when it comes from that. So if I go back to that last slide, whoops, sorry about that. If I go back to that last slide somehow, I couldn't have said 8 centimeters minus 12 because that gives us a negative number. This is our first formula. X final minus x initial equals change of distance. D equals distance. Go ahead, please, and write that in on 1C. I want you to have that formula. All right, cool. We're good with that. All right, going back to our first page here. On 1D, what do you think is the difference between position and distance? Position means where you are. Where you are. And distance means how far you have traveled. All right, excellent. How long did it take the car to travel? Well, if we go back up here and look at our graph, we can see we only have data through 9 seconds. So we don't know what happens after that. And also, we can also look at our data table to figure that out. We only have 9 seconds worth of data. So we only know that the car has traveled for 9 seconds. Awesome. What is the vertical intercept on your graph? This is the traditional y-intercept that you have in math. But remember, be careful because now we're going to call that vertical intercept the position line, which is x. X is going up. All right, this question asks this. What is the vertical intercept of your graph? So the vertical intercept, where does it intercept this part? All right, this is vertical, up and down. Where does it intercept at? It intercepts at 2 centimeters. So what is it telling us? Wherever your vertical intercept is where your initial position is going to be of your car, right? Or whatever it is you're talking about. So 2 centimeters is telling us that this is my initial position. All right, that's my initial position. How are we doing so far? Are we getting all this? Okay, let's go on to the slope. Hopefully you got to try the slope. All right, if you remember when we're finding slope, we always look for 2 points on the line. So this is my red line here, where it intersects the corner of the box, corner of the grid. So for this one, I'm going to use, this one, and I'm going to use this one. You can choose any point you want, just as long as it intersects the corner of the box. We're talking about the red line there. After I have my 2 dots, I'm going to go ahead and draw a triangle. And then I'm going to shade that triangle in. That's a new step. I don't think I've had you do that in the past, but I am now. Okay, I'm just doing rise over run. I count my boxes. 1, 2. I've got 2 boxes up, which is my rise. I've got 1, 2, 2 boxes over, which is my run. So I'm going to write this like this. 2 over 2. And we know we can't have any fractions in physics, so I have to break that down. 2 divided by 2. That equals 1, 1, right? But the other thing in physics we know is that you can't have any naked numbers. So watch this. How do I figure out what the units are? I know that my rise goes up. So I'm going to follow this up to the top there, and I know that that's meters. And then I'm going to follow my run over to here, and I see that that's seconds. All right, so I've got 1 meter per second. Okay, excellent. Go ahead. If you haven't, hopefully on 2B you found this already, but find 2 points on your slope, on your red line, where they intersect the exact corner of a box. It's hard to do. This one's a little bit tougher than the others. I'm going to start here and I go up in the very corner, okay, and I'm going to go up, and I'm seeing that none, no, that's not a full box. But when I get to almost the very end at 10 seconds and 300 meters, that looks to me like it's intersecting a full corner of the box. So I'm going to put a dot there. The only one that I see is this in the corner. You could always use this if it's at 0, 0. That one. All right? So that's my box. I'm going to draw my triangle. I'm going to shade it in. And I'm going to count my rise over run boxes. It looks to me like I 1, 2, 3 boxes up. 1, 2, 3, 4, 5 boxes over. So I've got 3 over 5. All right, so you know we don't like 3 over 5. So I've got to take out my calculator and do 3 divided by 5. And actually, I need a second to grab a calculator. I think it comes out to 0.6, but I'm just going to double check the math here. 3 divided by 5 is 0.6. Good. I was right. So 0.6, oops. All right, 0.6. And I'm going to go up to the top of my vertical to look at what my rise units are, and that's meters. And then I'm going to look across to see what my run units are, and they're minutes. I've got 0.6 meters per minute. Hopefully we're starting to get the hang of this now. We're going to do a short quiz on Monday when you get back over this stuff. So hopefully it's starting to come together, and if not, come see us quickly for help. All right, now we're down on here on 2C. Find 2 spots on the line, 2 points on the line where it intersects the corner of a grid line. So I'm going to pick here, and I'm going to pick here. I'm going to draw my triangle. I'm going to shade it in. And I'm going to count my rise boxes over my run boxes. So I'm going to go up 1, and I'm going to count my run is 1. So my rise was 1, and my run was 1. So I've got 1 over 1. Oops. 1 over 1, and then I'm going to look for my units. I know that 1 divided by 1 is 1, and my units on the vertical axis is centimeters, and on the horizontal axis is seconds. 1 centimeter per second. Okay, we're on the very last one. The last unit, skip that part. What do you think slope of a position versus time graph means? Now, if you remember from your bubble tube lab, we know the slope of a position versus time graph shows us speed. So hopefully you had speed there. All right, but there's one other thing that it shows us. And I want to come back to all these graphs here. Go back to our first page. Right? What direction was this object going? In a positive direction. So not only do they show us speed, but they also show us direction. Graphs show us speed with direction. So on here, I'm also going to put, sorry about that, direction. Oops. Now, speed with direction has a really important name that we're going to start calling. Instead of saying that slopes show speed, we're going to use the word velocity. Velocity means you have speed with direction. Baseball pitchers, they talk about velocity a lot. It's the speed of the ball, but also the movement, whether it's a sinker or a curved ball, or if it's in the right-hand corner of the plate. That's the direction the ball is going.